As of June 2024, the state of California boasts a cumulative solar power capacity that's enough to power nearly 15 million homes. In California, solar energy currently supplies roughly 31% of its electricity needs, making California the leading state in solar power generation in the United States. And it's not just California. Across the U.S. and across the world, solar power systems are increasingly critical to modern power grids. But their cybersecurity, it remains inefficient, posing risks to grid stability and national security. While individual residential systems produce limited power, their cumulative output is substantial, making vulnerabilities in the sector especially concerning. There's a new report from ForeScout, and it focuses on this issue. The research highlights how attackers can exploit weak authentication, hard-coded credentials, and insecure protocols such as MQTT and HTTP to take control of those inverters, disable them, and modify their output. Some vulnerabilities enable account takeovers or code execution on the inverters via malicious commands. Others involve cloud-side flaws such as unrestricted file uploads. In addition to potential grid impact, the vulnerabilities expose consumer privacy concerns such as leaked personal data and energy usage patterns, which could be used to build behavioral profiles of the users. The generic nature of the inverters amplifies the risk across regions and vendors. This is a story about the critical vulnerabilities being found in inverters and cloud systems used by the solar power industry, and what steps we should be taking today to secure them for tomorrow. I'm Robert Famosi. This is Error Code.
I am Daniel Santos, the head of research at ForeScout's Vedere Lab. So ForeScout is a cybersecurity vendor, and we deal with device visibility and control. So we basically understand every device in the network, what's the risk that it brings to an organization, and how you can detect and respond to threats on those devices.
About a year ago, in episode 43, I spoke with Dan Bertie of Bitdefender about hacking solar panels, among other things. With Daniel, we're going to get into the details of such attack. And I'm curious how he and ForeScout decided to go down the path of looking at solar panels in particular.
So actually last year at RSA 2024, we've had some customers, prospects, people at the event approach us and tell us, this is something interesting that's going on. People are starting to look into solar panels. It's starting to be something that is more and more common on power grids throughout the world. And I think that there is room for doing some deeper research there, right? And then we also started reading the news, and a lot of people were talking about that. There were some other security researchers that looked into these kinds of vulnerabilities as well. We thought, well, maybe we can do something there as well. More or less 6 months from research to disclosure to actually publishing the actual report.
So we're going to talk a lot about inverters. I asked Daniel to define what that is and how important it is to power grids. We're not necessarily talking about the solar panels themselves, but the process of transferring that energy from one place to another.
The inverter is the smart piece, let's say, of the ecosystem there, right? That takes the power that is generated by the solar panels and transforms that into AC. So the DC power that's generated transforms that into AC power so that it can be injected in the grid and used by household appliances and the rest of the power grid, let's say, right? But why is it a smart component? It could be a dumb, let's say, component as well, and doing that only electrically or electronically. But many inverters these days allow for remote monitoring and remote management, right? And that's why they have to be smart. They have to connect to clouds. They have to allow users to program them to switch on and off and have different safety settings and power settings and so on. And it's quite interesting that these days, this type of management is often enabled by a vendor supplied cloud. So that introduces lots of different points in this ecosystem, right? So you have the inverters, you have the cloud, you have the web applications, the mobile applications, and so on that actually connect to these inverters.
So in this report, there are a fair number of CVEs cited. There are also FSCTs. What are those?
Yeah, so FSCT is an internal ID that we assign to some of the vulnerabilities. Actually, the fact is we're still waiting for some CV IDs. It's the Grovat case, actually, right, described in the report. It's just the backlog of some of the agencies that assign these numbers is growing every day. Number of vulnerabilities is growing every day. It takes some time, and sometimes we wait until everything is done to make sure we publish a report when we have all the ideas. Sometimes we have a set date and we need to publish things because we deal with multiple vendors and so on, and we go ahead and we can update things later on, right? So FSCT is just, it stands for ForeScout. It's our internal search, let's say, and that's how we assign our identifiers to things.
Daniel's research focused on the inverter, both the physical device and the cloud. This report identifies 46 new vulnerabilities in systems from major manufacturers such as SunGrow, GoRot, and SMA, including a catalog of 93 known issues, a majority of which are high or critical in severity.
It was focused on the cloud applications connecting to the inverters, and some of the vulnerabilities are on the inverters themselves, some of the vulnerabilities are on the cloud side or the communications and so on. At the end of the day, they affect the inverters because that's, as an attacker, for the type of attacker model that we were looking at, that's what you want to hit in a way, but there are different ways to hit that, right? Either directly on an inverter or via the cloud accounts.
So these vulnerabilities, they would apply to large grids that you see out in the middle of nowhere, sending power to a city. Or would it apply to homes as well?
In the report, we defined, or others have defined as well, but we use this definition in the report of 3 types of solar installations, right? So you have the residential installations, which are the small rooftop installations that people are used to seeing. And that's the vast majority in terms of quantity of inverters these days, right? Most of them in the US, it's more than 95%, I believe, the last statistic I saw, are house or residential installations. Then you have commercial installations, which are similar to residential, but apply to businesses like hospitals, government facilities, manufacturing plants, and so on. They'll have their own rooftop installations as well. And then you have the utility scale or industry scale kind of solar parks, solar farms, and so on, that are the big ones, as you mentioned, that in the middle of somewhere in a desert or somewhere connecting to the grid in a city, right? So typically the residential and commercial installations will be often managed by these vendor clouds. And sometimes the industry or utilities installations will also be managed by a vendor cloud. But sometimes it will be directly connected to a utilities control center and so on. So utilities tend to have a bit of different security requirements and security architectures for their own installations.
So I want to understand this process a little better. The sun is beating down, and there's a photoelectric panel. It's converting raw sunlight, into electrons. That's direct current, or DC. To connect to a power grid, however, it needs to be alternating current, or AC. So you need an inverter. Today, that flow, that process, well, it's kind of irregular. A cloud passes in front of the sun, output dissipates. So the inverter helps regulate that flow. They're trying to control how much energy gets on the grid and how often it gets there.
Yeah, exactly. That's the kind of thing that is managed by the inverter, right? So when to inject power in the grid, when to use it in the house, and so on, because there are safety reasons for that as well. That when the grid has different types of demand, you may want or not want as a utility that more or less solar power is actually injected into the grid to make it stable, right? The whole point of the power grid is that most of it is not controlled in this way. Most of the generation is still controlled from large power plants that are, thermoelectric or hydroelectric or other kinds of power generation. And you need to balance out the demand, the generation, what's coming from solar, what's coming from other resources, and so on. And usually this control was done in the past directly by the utilities because they manage the large power plants. But now with the distributed nature of solar energy, there has to be a way to also be able to manage that, right? Either the users directly or in some cases the utilities. And that's why there are, as I mentioned, safety settings in some of the inverters or the way that it can be controlled how much power is actually output into the grid, right? And that's what allows some of the attacks where you can change the settings on those inverters and inject more when you shouldn't be injecting more, for instance.
So in other words, with the inverter, you can literally turn off a solar panel. You could say, hey, I don't want any more power at this time.
Exactly. Not turn off the panel itself, but turn off the inverter indeed, right? So there are possibilities to turn off the inverters, turn them on or turn them on with a different output setting. Depends, of course, on the inverter, what kind of capabilities it has, but in general, yes, it's possible to do that.
Some of the consequences could be that they could obtain some information about the users, email addresses, account info, and so forth.
Yeah, indeed. We also saw this other part, this other type of vulnerability, which is not just about taking control of things, not about just, potentially damaging the grid or running malicious code or something like that. It's more about users' privacy, right? And there are different levels of privacy there. One thing is people's addresses, let's say the fact that they have a device and so on. Another thing is their energy consumption or production, or in the case of EV chargers, for instance, that are connected to the same account in one of the vendors at least, you could see when it's on and off and what it has been, what kind of power it has supplied to the electric vehicle there and so on. So you can even in some cases build a profile of users' activities, right? That's a bit concerning in terms of privacy for sure, beyond just the fact that you can get people's addresses, email addresses, physical addresses, and kind of contact information.
Getting PII, well, that's an issue in Europe, for example, with GDPR, which I happen to think is a great law, and I don't understand why the United States doesn't have something similar. But there's other examples of the consequences, and one of the things they cite is ransomware.
Yeah, we looked at ransomware from a different point of view, right? And this is a kind of a line of work that we've been doing for a while. When we deal with embedded devices, IoT and OT and so on, ransomware doesn't always mean encrypting data, right? The typical kind of ransomware. So, because typically when we say ransomware, that's what comes to people's minds. But ransomware means using malicious software to demand a ransom, right? And that can be achieved in other ways, right? So basically, with a threat of switching off a device or with a threat of having control over a device and not restoring it to a state where it's safe and clean and used to and safe to be used, let's say, right? So the scenario of ransomware that we discussed here is basically if an attacker has control over a fleet of inverters, and that has the potential to the attacker has the potential to switch off or switch on some of these inverters in specific times. That could cause energy price fluctuations, for instance, or that could cause instability on the grid and so on. So the threat of doing some of those things would potentially mean that the attacker can demand a ransom from a utility to avoid this kind of consequence, right? So if you think in financial terms, really, you have control over a certain amount of inverters. If those inverters go down, the utility has to use backup generation power, which will probably be more expensive to them than the power that they are getting from the inverters at the time, right? So it's really a mathematical or financial calculation there. Do we pay the attacker or do we go and switch on our backup power generation, which is somewhat similar in the IT world. Do I want to pay the attacker or do I restore my backup or do I go on my network and go through the whole containment eradication of malware and so on? How much will that cost me versus just paying the attacker directly and getting my systems back?
Given this, I'm imagining that this is more of a criminal organization rather than a nation state.
Yeah, so typically when you talk about ransomware, about financial gains, it is something that criminals are looking into rather than countries or nations that have their own way of supporting their cyber operations, right, through their military or civilian intelligence agencies, for instance. There are cases, for instance, North Korea is known to employ APTs and state-sponsored actors to actually get some money as well because of sanctions and things like that. So it's not entirely impossible that a state actor would be looking for financial gain, but typically this is something that cyber criminals would look into. Yeah.
I guess I'm thinking about the Mirai botnet and surveillance cameras. Is there an opportunity here?
Now, it's actually interesting that there have been cases of botnets on solar power equipment, not on the inverters themselves directly, but on things like data loggers and monitoring systems and so on that are connected to the inverters and do this cloud communication that we discussed before for telemetry or for control for things like that, right? So there have been examples. There was a somewhat famous example in Japan last year where 800 devices were hijacked by a botnet. There was also there is a report from CISA talking about one of the Typhoon APTs in the U.S. critical infrastructure. And I believe it's Flex Typhoon. And what they were doing mostly is building botnets so that other threat actors could use those botnets to carry out their attacks. And there is a list of CVEs that CISA has shared, where some of those CVEs are the CVEs that were exploited by botnets as well, right, on those solar monitoring devices. So there are for sure cases of botnets that reach solar power devices, and it is something that can be used again either by cyber criminals to launch DDoS attacks, to rent those as residential proxies or things like that, or state-sponsored actors to mask further attacks, right, as in the case of Flex Typhoon that I just mentioned.
So far, we spent a lot of time on the inverter. Are there interesting things happening in the cloud that we haven't discussed?
Yeah, most of the interesting things on the cloud are the data leaks that I mentioned that we discussed, right? That there is the potential to get people's information that's stored directly on the cloud and not on the inverters, and the fact that you can use the clouds to get control of the inverters. Let's say that's mostly what we were looking into. There could be other attack scenarios that where the goal is not necessarily to control inverters or to have anything to do with the inverters, but it's on the vendors themselves, on the cloud themselves. We didn't explore those. It's an interesting maybe follow-up indeed, right? Like what can you do with the cloud if you're not looking to take control of an inverter?
So there are various types of attacks and relating to various vulnerabilities. And within the report was my old friend, the protocol MQTT. I mean, it comes up a lot in IoT. And this is an example of a very old protocol that has been used today in untoward ways. Are there other protocols that are being enlisted in the vulnerabilities that ForeScout found?
Yeah, so most of what we saw is either via traditional HTTP or MQTT. In these settings, people also use Modbus, which is also a very well-known protocol in the OT world, but that's usually for the communication between some inverters have external communication dongles that do the cloud communication, and the communication between the communication dongle and the inverter is done with Modbus. That's a typical scenario in this case, but we didn't look into those kinds of communications if there would be any vulnerability there. Many times this is even local serial communication, so it was kind of outside our attacker model. But yeah, MQTT and HTTP are the ones that popped up the most. Often MQTT for telemetry and commands, and HTTP for user interaction with the cloud or with the web or mobile applications.
Again, MQTT, not surprising, because as I said, it shows up in a lot of IoT products. Is it just because it's off the shelf, or does it uniquely satisfy a need?
I don't know if it uniquely satisfies, but it's a very common design pattern, let's put it this way, for device fleet management these days, right? And oftentimes we see that in embedded devices, IoT, OT out there. One vendor, a couple of vendors comes up with a solution, many will adopt the same kind of solution, right? Whether it's copying things or just thinking the same way engineers will think similarly. There are some protocols that will be more, let's say, useful for certain types of applications. So With MQTT, that's the case. We see it's not just for the inverters. In some cases, for EV chargers and other types of devices as well, they send telemetry and they receive commands via MQTT. It could be done differently. It could be done with other protocols directly, more point to point, let's say, or client server, rather than this kind of publish subscribe. But it does satisfy a need to do this kind of fleet management, right?
So I asked Daniel if these inverters are kind of white label, like they're not proprietary, right?
They are not usually owned or manufactured by a utility, right? They are manufactured by the companies that specialize in inverters and other types of distributed energy resources or EV chargers or this kind of smart energy kind of appliances. They are, in theory, they can be used in different, depending on the settings, but they can be used in different grids throughout the world, and they are often exported throughout the world. So you'll have in the Netherlands and in the US and in Japan or China or other countries throughout the world, the same or very similar kinds of inverters from very similar manufacturers.
So it is possible that a vulnerability in one will propagate out to many.
Yeah, indeed. That's what we find, right? That it's not tied to a specific utility or specific local grid or something like that. It's something that is throughout the world, let's say, in different kinds of inverters. Typically, what will happen is that some of these vendors will have different clouds, local clouds, let's say, to manage those inverters locally. That's not always the case, but it's oftentimes the case. But that has to do with data protection or things like that, more than any sort of technical requirement. And the inverters themselves, at the end of the day, that sit on the power grid are the same.
I'm also wondering if Daniel's finding the homogenization of OT is helping or hindering the security process. In other words, with less proprietary stuff, are we seeing more large-scale attacks because they're using Linux?
That's also a very interesting question. I think that, yes, the more standardized platforms, protocols, and frameworks and everything else, technology that people use, the less chance there is for individual mistakes to happen. Let's put it this way, right? From individual vendors. Let's put it very clearly. There's a reason why you don't or you shouldn't implement cryptography in-house, right? You should use things that are well known, well tested, well developed by others who are experts in that. Same thing for operating systems, right? You can get an operating system, Linux, you mentioned. It's a great example. The whole community is looking at Linux. Yes, there are vulnerabilities and so on, but it's because a lot of people are looking into that. So I think that, yes, that is something that should improve security for the communication protocols as well, right? A lot of the OT communication protocols are still unencrypted, unauthenticated things that were designed long ago by specific vendors. And as we move into things like OPC UA and so on, that's much more standardized, open, and potentially deployed more securely, that would be better.
And again, with homogenization, does it create the potential for much larger attacks? Because you're no longer niche. You're no longer working security by obscurity.
That's the other side of the coin there, right? In the sense that you mentioned before the botnets, for instance, that run on Linux, right? They wouldn't run on a PLC that runs, I don't know, FreeRTOS or whatever other RTOS you're looking at, but they would run on a PLC with Linux potentially, right? Depending on architectures and so on. So yes, that's the other side of it. I do think it's still a valid trade-off where if you use things that are less prone to vulnerabilities, yes, sorry, not less prone, but less, they have been more researched and therefore they potentially have less things to be discovered. If something is discovered and there is a vulnerability and something is exploited and something runs on that, yes, it's a trade-off, but still you have on the other side better security by design.
Don't want to be geocentric here. So what is the European counterpart to the United States CISA?
Yeah, it's I would say it's ENISA. It's the European Agency for Information Security. They are more or less the counterpart. They have some different types of mandates for some different kinds of things, but it's their role also to look into information security for Europe and critical infrastructure security and so on. There is an initiative for a European CERT. which was also, something that CISA did with the ICS cert, and they published vulnerabilities and so on. So that would be the counterpart. It's not a one-to-one mapping. It's not exactly the same thing, but that would be the counterpart.
So again, given that there are these identified vulnerabilities, what would be a typical attack scenario?
Yeah, so it's interesting that, as we mentioned before, there are different vulnerabilities in different parts of the ecosystem, right? So some of them are on the inverter, some of them are on the cloud applications, on the web or mobile applications, and so on. So a very simple one that actually, interestingly, doesn't necessarily affect the inverters directly, but just one of the vendors, kind of their cloud infrastructure, was just the ability to upload unrestricted file types to their server, right? So basically, you get code execution on that server directly because they don't check the kind of file that you're uploading. So you can upload like a web shell or something like that that will give you control over that. And that's a part of this research that is actually quite interesting as well. We didn't go into much more detail into that. We didn't expand on this too much, but the infrastructure of those inverter manufacturers is oftentimes vulnerable as well. We did see a few examples of exposed services that shouldn't be exposed and things like that. We didn't do pen testing on the vendors themselves, let's say. So that was not our goal to go too further there. But it's something that was a little bit alarming, right? But the most interesting stuff really is what allows us to take control of an inverter and switch it on or off, or basically change settings or execute code on those inverters, right? So on the Grovat vendor, what we saw is that simply with the cloud interactions, you could fully take control of another user's account, or basically take those devices that are assigned to that user and assigned it to you as an attacker. And from there, just with GUI management or with API calls, do the whole switching on and off and changing inverters and so on. On the other vendor, SunGrow, it was a little bit more involved, the attack path, where we actually had to exploit some of the things you mentioned before with MQTT, for instance, to actually send MQTT messages to potentially many inverters at the same time. And some of those messages could be malicious and exploit a local vulnerability on the inverters to then execute code, right? So basically, there was a hard-coded credential that allowed us to send these messages to many inverters. There was a vulnerability on the cloud that allowed us to get the serial numbers of those inverters, so it allows us to identify them, to know who to send the messages to via the MQTT broker. And there was a local vulnerability on the communication dongle on the inverter that allowed us to execute code, right? So if you chain those things together, you get a lot of serial numbers, you instruct the broker to send a message to all those serial numbers, and that message is malicious to basically execute code on an inverter, right? So there are different levels of complexity, let's say, of exploiting these things, but at the end of the day, depending on the vendor that you're targeting and depending on the level of complexity of the attack you want to achieve, there are multiple ways to take control of these inverters.
And what has been the response from the vendors that you tested?
Response from the vendors, which in the beginning, honestly, it felt like we wouldn't get anywhere with some of the vendors. Like, we're not sure that they would be able to fix issues, that they had the right level of security maturity. But within this 6 months, more or less, of the research, we were able to get pretty good responses and to involve CISA in the coordination and other agencies in Europe as well. And get the vendors to fix things, and it became a very collaborative process also, right? So that I think that's really a great win. And like I said, there has been other research in the past that looked into these types of vulnerabilities, and there will probably be other research pieces in the future that look into those kinds of issues as well. But as we kind of find more issues, bring more vendors up to speed, this should help the whole community, right? A lot of the work that we've done is on the operational technology side of things, and that is always, the typical excuse, let's say, or the typical issue there is, oh, this was designed 20 years ago, this has been in place for 30 years, it takes a whole redesign to fix issues and so on. So now we chose a target, or we chose a field of study where things are much newer, right? And hopefully things can be fixed faster before, 30 years from now, we look back and we say, oh, we should have fixed those things in 2025, right?
Daniel mentioned working with these newer companies and the response from them. I imagine initially they were kind of like, what? No. But Daniel says they came up to speed fairly quickly. Clearly, they recognized the market value in being able to have security in a product.
Yeah, I think so. I think they are. I think it's not something you can ignore anymore in any market, right? Cybersecurity, and it becomes fairly apparent when you are ignoring things. Some very independent researchers sometimes find issues, and they maybe don't have the right kind of pressure, maybe the word, but like they don't know how to react. Also, if a vendor doesn't know how to react, right? It really has to be something that somebody has a little bit more experience there and can manage the process in a way to reach this coordinated vulnerability disclosure. So that's the fact when you include a coordination agency like CISA, or when you're working with researchers like us who have done this in the past with other companies, and it's never threatening the company like, look, we will just publish this and whatever you do, right? It's more about like, look, your customers are going to be exposed if you don't fix. It's really an important thing that you do. We work with timelines that are flexible also, right? Like typically the industry says it's a 90-day window for vulnerability disclosure. This took more than 90 days, and usually it's okay as long as we have a commitment from the vendor that things will be fixed. It's not a problem to wait a little bit longer, right? So yes, I would say that they realized the value or the necessity of taking cybersecurity seriously and responding to things. And they fairly quickly managed to set up the teams that they needed to respond to that and to make sure that the public is aware of what's going on as well.
Revisiting that question, are there some of these companies seeing it as a good thing to say that they've had those vulnerabilities fixed in their product? They've been tested by outside sources.
That's a great question. It's a very interesting question. I didn't see that yet on specifically the solar market. On the OT market, it's something that I wouldn't use the word specifically like, we've been tested by others, so we are more secure or something. But there is this notion growing in the OT community that not necessarily because you have more vulnerabilities published, you are less secure or something like that. It could be actually otherwise, right? And I always cite this example of a company that we've worked with many times in vulnerability disclosure, and they've always been great. It's Siemens. And Siemens actually has the highest number of published vulnerabilities on CISA of the OT equipment vendor. Doesn't mean they're less secure. It means they're publishing more vulnerabilities. That's all. You can't really infer the fact that they are less secure, right? So I think it would be great for some solar companies to maybe take this lead as well and be the ones saying, okay, we're gonna be the ones publishing more vulnerabilities because they are there, people will find them, they will fix them, and then we will become more secure. I think that there's also a connection here with things like bug bounty programs, right? Where that's fairly common in IT these days, where you expose your website, your application, whatever, to independent researchers out there. They come, they find issues, you reward them because of their time and so on, the impact that they have. But you also have this kind of seal of approval saying, yeah, I've been tested out there in the public, and these are the issues that were found, and we fixed them.
So given everything we've discussed, it seems like the common answer in OT and IoT is to just simply put security controls in place. But are there some other best practices that somebody might want to employ?
It's interesting that as this kind of research, this kind of device is quite recent. It's kind of a hot topic, let's say, like a lot of people are discussing security here. There's a lot of very recent publications that help with this risk mitigation side as well. So the NIST released at the end of last year, the end of 2024, a cybersecurity guideline for owners of smart inverters, right? Whether it's residential or commercial and so on. And they go through all of the usual update your software, have backups in place, make sure it's not directly exposed on the internet, change default credentials, these kinds of things, right? If you're a commercial deployer or commercial user of these inverters, make sure that it's not connected to the rest of your critical devices, that an attack there would lead to an attack on the rest of your network, things like that. It's also interesting that there is a lot that the manufacturers of those devices have to do and to kind of to improve on in terms of security, right? And this kind of research helps them to improve as well. But we looked at 6 manufacturers and found issues in 3. For sure, there are many other manufacturers out there that still need to be evaluated either internally or externally by independent researchers to find their security issues, right? So I would say that the procurement side of things, right? Like what kind of device am I putting in my house or in my business, or is the utility using in their own solar parks? That is something very important, right? What is the manufacturer behind that? What's their kind of security maturity? What's their security development life cycle type of requirements and certifications and response to cybersecurity and so on and so on. With some of the manufacturers we dealt with, it was the first time that they were doing security response, actually, or responsible disclosure, right? So again, that's a great win, I think, for the community. It means that now they're ready to do it again and again with other researchers, because it's something that happens. Vulnerabilities happen. We know it's probably not ever going to be the case that devices don't have vulnerabilities. It's all about how the vendors deal with that, right? So yeah, I think that this is one kind of example where there's much that a user can do, but the user also has to trust the manufacturer that they are doing the right things in terms of security. And there's also a role here for regulators, right? What kinds of devices do they allow to be connected to the grid? Because as we mentioned in the report, this is something that potentially is a national security concern, right? If the grid goes down, if there are instabilities, if there are blackouts or whatever, or disturbances that don't lead to a blackout, but people have to respond to that. It's quite problematic, right? So regulators should pay attention to what kinds of devices can be deployed or sold in a specific country.
So do they currently have those regulations?
It's evolving in different places in the world. As far as I know, in the US, there isn't any specific ban on any specific type of device. There was some discussion about Huawei in the past, just because of the fact that they were banned from communications equipment, and they are also a large inverter manufacturer. But Huawei decided to just voluntarily leave the US market at that point. In Europe, there are some initiatives now to ban remote management from potentially unfriendly countries. And it's something that's popping up in different places. I know that in the UK specifically, the MI5 was about to look into the devices that are manufactured in China and what's the potential problems they could bring to the grid in the UK and so on. So in different places in the world, there are different types of regulations, or at least activity into looking into the sources of those devices and what kind of vulnerabilities they can contain and what that means for the grid, right? But really hard bans, let's say, on the devices, it's just really emerging right now.
I'd like to thank Daniel for coming on the show and talking about the new report from ForeScout on vulnerabilities found in solar panel inverters. The conversation centered around the role of inverters in solar energy systems, and particularly their transformation from simple electrical devices to smart components within the broader cloud-connected ecosystem. Modern inverters not only convert DC power from solar panels to AC power for grid use, but allow for remote monitoring, control, and configuration via vendor-managed cloud platforms. These platforms introduce new vulnerabilities, with attack surfaces spanning from the physical devices themselves to the cloud applications to communication protocols. Hey, if you're enjoying Error Code, tell a friend. I'm sure there are other people out there who like narrative information security podcasts. And I'd really like to hear from you. Go to errorcodepodcast.com to get more details. And tell me what you like, and even what you don't. I've got some great episodes coming up. I'll have more on hacking water facilities. Subscribe today. I don't want you to miss out.